Okay, here's a wild thought for you. What if friction, the force that we always think of as slowing things down, could actually generate power? It's a concept that sounds like it breaks the rules, but it actually pulls back the curtain on a really bizarre and fascinating corner of the quantum world. So, let's dive in.
So here's the question at the heart of all this, the one that's had scientists scratching their heads for years. On the surface, it sounds simple enough, right? But the answer, well, it takes us deep into some pretty strange territory. Can a liquid, just flowing over a surface, really create electricity?
And this is the basic setup from the experiments. You have a completely neutral liquid, and that's the key here. It has no free ions floating around to carry a charge, and it's just flowing over a conductive material. But somehow, an electrical current pops into existence in the solid. That's the whole puzzle. If there are no ions, where on earth is the electricity coming from? All right, so let's start unpacking this thing. What we're dealing with here is a genuine quantum puzzle, a current that's created purely by flow. Now, I want to be super clear. This isn't just some theory on a whiteboard. Researchers have actually seen this in their labs. They've measured a real, tangible electric current. The big problem was, for the longest time, nobody could explain why it was happening. All the usual explanations from classical physics just completely fell apart.
So, like any good mystery, the first thing scientists had to do was eliminate the obvious suspects. They had to go down the list and rule out all the old, established theories one by one.
And here are the usual suspects. You've got streaming potential, which is a common way to get current from flow, but nope, that needs ions, and we already know our liquid is ion-free. The other classical ideas also relied on things that just weren't there in these experiments. So it was clear they were looking at something brand new. Okay, so if the old physics rulebook doesn't work, we're going to need a new one. And the first real clue comes from this fascinating quantum idea called hydrodynamic drag. Okay, this is absolutely the crucial idea. It's called hydrodynamic Coulomb drag. The best way to picture it is something we already see in electronics. If you have a current flowing in one wire, it can actually drag electrons along in a parallel wire right next to it without ever touching. This new theory asks, what if a flowing liquid could do the exact same thing to the electrons inside the solid it's sliding over?
This means we have to zoom in. Way in. The real answer isn't about the big, visible properties of the liquid or the solid. It's hidden in the quantum-level chatter, these incredibly fast, invisible interactions happening right at that boundary between the liquid and the solid's ocean of electrons.
And this brings us right to the main characters of our story. Let's meet the two specific quantum draggers that are actually doing the work of pulling these electrons along for the ride. So it turns out there are two main ways this quantum drag happens. First, you've got direct drag, where the liquid itself is directly pulling on the electrons. Then there's phonon drag, which is a bit more of an indirect two-step process. The liquid starts a vibration, and then the vibration pushes the electrons.
So let's look at direct drag first. Thanks to quantum mechanics, even in a totally neutral liquid, you get these tiny, temporary ripples of positive and negative charge constantly blinking in and out of existence. The theory calls these little fluctuations hydrants. As the liquid flows, these moving hydrants act like tiny little magnets, exerting a direct pull on the electrons in the solid and dragging them right along with the flow.
The second method is phonon drag, and this one is all about vibration. The physical movement of the liquid rubbing across the surface actually makes the solid's atomic structure, its crystal lattice, start to vibrate. These vibrations come in little packets of energy called phonons. So you can almost picture the liquid creating a phonon wind inside the solid that just blows the electrons forward. So a neutral liquid can generate electricity just by moving, all thanks to quantum mechanics. That's mind-bending enough. But believe it or not, this story has an even weirder, more powerful twist.
Because this new current, it doesn't just sit there, it actively changes the very system that created it, and that leads to a side effect that is completely counterintuitive.
And here it is, the big reveal, the quantum feedback loop. The current of electrons gets dragged along by the liquid. But if the conditions are right, those electrons can actually start moving faster than the liquid that's dragging them. When that happens, the roles completely reverse. The electrons start pushing back on the liquid, creating a repulsive force. This is negative friction. The system is literally making itself more slippery.
So the takeaway is this quantum feedback mechanism. The current that was generated by the flow actually fights back against the very friction that created it, and that reduces the total drag. The system essentially learns to lubricate itself at the quantum level. It's just a beautiful, self-regulating loop.
Now, this is way more than just a weird physics curiosity. This discovery opens the door to actually engineering a future that is quite literally a lot more slippery.
And we're not talking about a tiny effect here. The research shows that for a material like graphene, this quantum feedback could cut friction by about 12%. That's pretty good. But for a specially engineered material called a 2D electron gas, which is basically an electron superhighway, that reduction could be as high as 80%. That is a monumental shift in how a surface behaves. So why does all this matter? It means we can start designing surfaces with almost no friction, right from the quantum level up. This could revolutionize everything from moving fluids around inside tiny computer chips to creating incredibly efficient water purification systems. It's a whole new bridge between two different fields of physics.
And you know, the researchers who figured this out put it perfectly, I think. They said, quantum effects can become valuable assets for future water technologies. This is all about taking a quantum mystery and turning it into a powerful, practical tool.
Which really leaves us with one final fascinating thought. We just looked at the simple boundary between a liquid and a solid and found this incredible hidden process. It just makes you wonder, how many other quantum secrets like this are hiding in plain sight, right there at the surface of things?